Okay, welcome back. And so now what we're going to do is we're going to look at this example here, and we're going to look at how the rows are related to each other. Okay, so I've got this matrix A, and then matrix D, matrix G, and matrix B. So this is our final matrix. So we're going from matrix A to matrix B. Okay, and so here are the elementary row operations already done for us. And notice how we've gone from this to the reduced echelon form, okay, for B. And so now what we want to do is we want to look at how the rows are related. So what I'm going to do is for matrix A, I'm going to represent each one of these rows by the letter alpha. So alpha 1 represents this row, alpha 2 represents the bottom row, row 2. Okay? So now if I go through the same steps, what happens here? Well, the relationship between the rows of A and B are as follows. Okay, or excuse me, A and D, I should say. And so if I look at the relationship after the first operation, which is just swapping the rows, I get the relationship to delta 1, right? So now we're going to use delta 1. So delta 1 is what? Is equal to alpha 2. And then delta 2 is equal to alpha 1. Okay, so that's D. Okay, now we're going to go to the next operation, which is just taking 1/2 of R2. So now we're dealing with gamma. Okay, so now we're going to use gamma, right? So we're dealing with G, so let's use gamma, lowercase gamma, to see the relationship of rows for matrix G and how these rows are related back to A. Okay, so now what's going on here? We're taking 1/2 of this one. So what does this mean? Well, it means that gamma 1 is equal to alpha 2, right? And what about, oh, hold on a second. Oh, sorry. These represent rows, so they have to be vectors. Right? They're row vectors. Okay, now, and then gamma 2, right? So gamma 2 is equal to 1/2 alpha 1. Right? That makes sense, right? And now finally, we have the elementary row operation. What are we doing? Oh, that's right. Negative R2 plus R1. And so since we're dealing with B, we're going to use beta. And so what happens to our rows now? Now we're going to do beta 1 and beta 2. And how are those related to alpha, or again, vectors? Okay. How are those related to the rows of alpha? Well, we're taking negative R2, so we're taking negative this and adding it to this. So if we take negative 1/2 alpha 1 and we're going to add it to alpha 2. So in other words, this is going to be, well, hold on a second. So beta 1, that's going to be unchanged. So that's just going to equal alpha 2 then. Vector alpha 2, right? Or hold on. Oh, no, I'm sorry. 2 is unchanged. So never mind. This is going to stay the same. So this is going to equal 1/2 alpha 1, right? That should stay the same. Yep. Because we're taking negative R2. I was thinking R1. So if we take negative R2 and add it to R1, so that means we're taking negative this and adding it to this. So that means that beta 1 is equal to alpha 2 vector minus 1/2 alpha 1 vector. So now here's the thing. Notice what's going on here. What Gauss's method is doing in doing these elementary row operations is it systematically finds a suitable sequence of linear combinations of the rows. Because notice here, we started with these 2 rows, right? These row vectors. And through these elementary row operations, what we found is we found a suitable linear combination of these row vectors in order to get to our final reduced echelon form. Okay? That's going to be important to remember. That's a key aspect. Talk to you later.